So our next proof will require one assumption or fact. Fact. This whole proof, the whole conversation we're about to have is taking place in a McDonald's drive-thru. We're in a McDonald's drive-thru and thirsty for some chicken McNuggets. This particular McDonald's sells McNuggets by the 4-piece and the 5-piece only. So for some reason we go to the McDonald's, we want chicken nuggets. We only get the 4-piece or the 5-piece. We have to make some decisions. How is it going to come to math? You'll see. Here's the claim. The claim is that there is some natural number n such that for all n and n, such that n is bigger than or equal to n. So for everything bigger than n, we can purchase exactly n nuggets from a combo of 4 and 5 pieces. It's a weird claim. And then there's some number n, so for everything bigger than that, we can purchase exactly that many nuggets from a combo of 4 and 5 pieces for every number bigger than that. So for example, right, like, let's just start writing down some numbers here. 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll back those off. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Give myself some room here. There we go. That'll be enough. So for example, 2, we cannot possibly purchase exactly 2 nuggets when they only offer 4 pieces and 5 pieces, right? The smallest we can purchase is 4. So we can't purchase any 2 pieces. We also can't purchase any 3 pieces. Or you're also going to purchase exactly 3 nuggets. But we can't purchase exactly 4 nuggets because 4 just equals 4. So we just order 1 4-piece. And we can't purchase exactly 5 nuggets because 5 just equals 5. Just 1 5-piece, please. 6, well, we run into an issue again, right? Because no matter how we combine a 4 and 5-piece, we cannot make exactly 6 nuggets. And same thing with 7. But 8, again, we can go, okay, wait, 8's 4 plus 4. So we can order 2 4-pieces and we'll get 8. So we can make exactly 8 nuggets. And we can make 9 too. 9's just 4. That's fine. How about 10? Easy, right? 10 just 5 plus 5. How about 11? We can't make 11. Right? No matter what we do, we cannot make 11. So this means that if there is a number n, just for all n bigger than n, we can make that number. That n's got to be bigger than 11, right? Because we can't make 11. What 12? Oh, well, 12, that's just 4 plus 4 plus 4, right? That's fine. Hey, 13 is one bigger than that. So that's just going to be 4 plus 4. Change one of those 4s to a 5. So we can make 13. 2 4-pieces and 5-piece. 14, oh, well, that's just one more. So we can change another one of those 4s to a 5. That's 4 plus 5 plus 5. And 15, Just one more, change that last 4 to a 5. So we get 5 plus 5 plus 5. Now I claim that we already have everything we need to prove the claim holds for everything bigger than 12. What? How? It feels like we just scratched the surface. How do you know it's going to work for 17, 18, 19? How do you know it's going to work for 37? Here's the idea. Let's look at 16. Can we make 16? Sure, we can make 16. Right? 16 is 4 plus 4 plus 4 plus 4. 4 fours. Totally fine. But here's the real idea. Can we make 16 building off a previous combo? Because if you think about it, if we know we can make a certain number, well, then we know we can make that number plus 4, make that number plus 5 or something like that, right? Make the number plus 8. Well, 16, you could do 8 plus 8, for example. We know we can make that because we know we can make 8, so we can make it twice, right? Just double that order. But still not exactly what I'm looking for. Instead, let's look at this. 16 is 12 plus 4. I like that a lot. We know we can make 12 because we just did it down here. Therefore, we can make 12 plus 4, just add an extra 4 piece to whatever this combination is. Not 17. Well, we could think of 17 as, for example, 9 plus 8. Once again, I think it's very useful. Instead, look at this. 17, that's just 13 plus 4. We know we can make 13. Just take whatever combo that is, add a 4 piece. Same with 18, that's going to be 14 plus 4. 19 is going to be 15 plus 4. 20 is going to be 16 plus 4. Do you see what's happening here? Once we've proven that it holds for 4 in a row, which we did from 12 to 15, we're guaranteed it'll work forever after that because we can always just make the next number by taking the combo from 4 previous and adding a 4 piece to it. So 16, you go 4 previous to 12, add 4. 17, you go 4 previous to 13, add 4. And we know that we can do this with 16 through 19 because 12 through 14 was satisfied. But that means we can do it from 20 to 23 because 16 through 19 is satisfied. This is like the induction right here. 12 through 15, those are the first 2 cranks to get it going. But after that, we just keep referencing previous ones and we keep filling in every single number. And we can show this for all numbers. This means that 1,300,112, we can make that with chicken nuggets. We know that to be a fact because of this right here. That's fascinating. And we're running out of time, so I was going to write out a very quick kind of proof sketch to show you how you do this. So our proof, there it is. Our proof is going to go like this. So we're going to prove by strong induction on n. Actually, first of all, right, technically I didn't say, I said there is some natural number n. So I'm going to say let n equal 12. Note 12 is a natural number. Because remember, in there exists proofs, you have to just verify. Yeah, 12 does fit the natural number mold. Now, proceed by proof by strong induction. Oh, I'm way off the screen. Proof by strong induction. All right. So here's how that goes. Remember, we always have our base cases, right? In our base cases, we want to show it holds. In our little thing we said we want to show it holds through 12 through 15. So once we get past 15, we can start proving it by referencing 4 back. But we can't do that until we get past 15. Because, for example, to reference 4 back from 15 was 11. And remember, we couldn't make it with 11. So this inductive argument doesn't start working until we have 4 previous ones, and it'll start working until we get to 15. So that means we have to prove it for 12, 13, 14, and 15. So let's go ahead and let n equal 12. I guess I should say this is proof by strong induction on n. There we go. Let's go ahead and let n equal 12. Yeah. Note 12 equals 4 plus 4 plus 4. So we can make 12. I'm not being very formal here because we're out of time and all that, but we can make 12. That means that we can order chicken McNuggets. We can make means we can do it. Let's go ahead and let n equal 13. Note 13 equals 4 plus 4 plus 5. So we can make 13. Let n equal 14. Note 14 equals 4 plus 5 plus 5. So we can make 14. Let's go ahead and let n equal to 15. Note 15 equals 5 plus 5 plus 5. So we can make 15. My 14 looks like an M. Weird. There we go. So this proves all of our base cases, right? 12 through 15, we're just verifying just through brute force that we can make them. That's totally fine. Also the inductive step. So the inductive step, remember, here's where we want to show that for all n, we want to go bigger than or equal to 15. Because we want to show everything up to 15, we can prove 16, because we can subtract 4. We can prove 17, so you can go back 4. Just keep doing that over and over again. So I want to show that for all n bigger than 15, that P of 12 and P of 13, all the way out to P of 15, P of n, will imply P of n plus 1. So once we get bigger than or equal to 15, the inductive argument starts working. We can say that everything up to n being true will prove that n is true. And notice, by the way, that even though we're only going to use the fourth back in our proof, we're not actually going to use any of the other previous cases, we still need strong induction rather than weak induction, because weak induction just says P of n implies P of n plus 1. But that's actually not enough for us. We don't know that P of n implies P of n plus 1. We know that if you go 4 back, P of n minus 3 or whatever will imply P of n plus 1. So we need to have all these in place. Anyway, in our particular case, what this is saying is i.e. for all n greater than or equal to 15, for all n bigger than 15, if we can make every k where 12 is less than or equal to k less than or equal to n, then we can make n plus 1. That's what we're trying to show, right? So, let's get down to business. Let's just go. Let n be any integer such that n is bigger than or equal to 15. Let's take a pause actually for a second. I think we take a pause. I feel like I'm going too fast. I took the time, I'm going even faster. Let's go. So we can make n plus 1. Let me be any integer such that n is greater than or equal to 15. Yeah. Now I want to show, now we have to make our inductive assumption, right? Assume, it's the inductive assumption that for every integer k such that 12 is equal to k less than or equal to n, we can make k. So now we want to show we can make n plus 1. That's the whole idea. If we can show that everything up to n implies we can make n plus 1, then we have the chain reaction effect on gold. And we can easily do this, right? Using this exact idea I was talking about, looking at the fourth previous and just adding 4. So let's go ahead and say consider n plus 1 minus 4. 4 less than n plus 1. Note that since n is greater than or equal to 15, n plus 1 is greater than or equal to 16. By adding 1 to both sides, I'm going to skip some steps here. Thus, n plus 1 minus 4 is greater than or equal to 12 by subtracting 4 from both sides. And that's incredibly important because, right, I'm going to start writing below the glare. That's incredibly important because we want n plus 1 minus 4 to be in our range where we can assume that we can make n plus 1 minus 4. We can assume the claim holds true for this. So let's go ahead and note that 12 is less than n plus 1 minus 4, which is less than or equal to n, clearly because it's n minus 3 less than n. And move down here. So we know that this number, n plus 1 minus 4, is between 12 and n. So by our inductive assumption, assuming that everything holds from 12 to n, right, or up to n, or we start at 12 in this case, by our inductive assumption, I'm going to say hypothesis this time. Same thing. By our inductive hypothesis, actually, yeah, but by our inductive hypothesis, we can make n plus 1 minus 4, since 12 is less than or equal to n plus 1 minus 4 less than or equal to n. That's all we can do. You don't have to write that twice. We just wrote it. I just did it for posterity's sake. We can make n plus 1 minus 4. Thus, we can make n plus 1 minus 4 plus 4, right? Because we just add an extra 4-piece chicken McNuggets. Keep your eye on the nuggets here, which equals n plus 1 minus 4 plus 4. Those cancel. This equals n plus 1. And we can do this, I'll say, it's not very formal, I'll say by adding a 4-piece to whatever combo made n plus 1 minus 4. We're so close. So now we can make n plus 1. Actually, this is exactly what I want to show. I want to show that if it holds up to n, we can make n plus 1, which we just showed we can. So that means we can move straight on to the conclusion. Which is, therefore, for all n in x in the natural and z such that x is bigger than or equal to 12, for all n in this range, we can make n. And just to bring it back, this was a there exists proof, saying there existed this number n, big N. I'll say ergo, just to be fancy, n equals 12 works. Done. So there's the idea, people. This is proof by strong induction. I hope you enjoyed this one. I mean, how cool is this thing, right? This idea that we can show you can make any number, literally any number. Take 3.1415926 trillion, right? Take that number, you can make that out of nuggets. And you can prove that starting at 12 with this really simple form, right? All you do is you say it works from 12 to 15. And then this argument shows that as long as n is bigger than or equal to 15, and it works everything up to n, we can prove n plus 1. well, 15 is bigger than or equal to 15, and everything works up to 15 from 12 to 15, so we can prove it for 16. Then 16 is bigger than or equal to 15, so this argument tells us as long as everything works up to 15, if we show it just did, then you can prove it for 17. Or, 17. You can prove it for 18. You can prove it for 19, 20, 21, 22. This right here instantly proves our entire logic chain we're talking about for this chain reaction happens. We've proven that we can make every single nugget number, that's a nice, it's a nice mathematical term, up to or after 12, including 12. And look at the time. Actually, I gotta watch. Look at the time. I gotta go. So I hope you guys enjoyed this lecture. As always, if you have any questions. But other than that, enjoy your weekend off without discrete math homework. We'll be back at it next week. But really, you only have like 3 homeworks left, 3 to 4, I think. It's kind of crazy how the year's coming to an end. But anyway, enjoy your weekend for now. And I'll see you guys later.